All right. So this is going to be your 4.1 and 4.2 lecture. This is the introduction to exponential functions, and we're going to talk about their graphs. Truth be told, 4.2 you could probably do right now, just because it's only transformational laws that we're talking about there in 4.2. But 4.1, you do have some experience with exponential functions. We're just going to draw that out a little bit more. Today what we're going to do is discern when a function is exponential and when it is linear. And we're going to not spend a whole lot of time on this, but we will definitely talk about it. This is going to be the big one. Writing exponential functions given a real-world context or coordinate pairs. Solving problems with compound interest. That's going to be a part, really, of two. That's going to be our main application. And then we're going to talk about Euler's number. Euler's number. It's spelled Euler, but it's pronounced Euler. One who oils. The Euler's number and continuous compounding interest. And then we're going to solve problems involving continuous growth using exponential functions, which is really only going to be like the baby of 3 and 4, basically. Well, 3 and 4 and 2. 2, 3, and 4 are going to have a baby, and that's going to be 5. So this is the definition of exponential functions. I find this definition a little clunky, but here's the important stuff I need you to know. They are going to look like this. This is what an exponential function is going to look like. A times b to the x power. A, we call that our, there's a few different ways that we can think about this. We can think about this as a starting point. Or a y-intercept. Okay with it there. And then b, on the other hand, this is going to be our growth / decay factor. Okay. Ultimately, whatever b is, if I think about like a growth or a decay factor as something that makes my y value either grow or shrink, what you could quite literally do is think about what happened here. Resume slideshow. Thank you. We're all figuring out the technology here. Is if I had something like y is equal to my starting point times my growth or decay factor, say to the 5th power, right? In this case, x is going to be equal to 5. And so what's really happening is my y value is 1a and 5 b's all multiplied together. So you'll see that that'll be helpful when we talk about percentages. Something that I want you to think about is, or a way to think about b is this here, this 1 plus r. R is going to be our growth rate or our decay rate, and the b value is just going to be taking 1 and adding or effectively subtracting from that. We'll talk more about that. So when is a function exponential and when is a function linear? So let's suppose company A has 100 stores and expands by opening 50 new stores a year. So let's just start with A. So here are our years. We're going up by 2 every time. So what we're really saying is we're adding 100 each and every time. Okay, we're adding 100 each and every time. Okay, which makes sense. You know, we're adding 2 years. We're supposed to be adding 50 a year. So there you go. Don't know why it's doing all that extra writing for me. So now, let's suppose instead we had company B that was actually increasing. We start with 100 stores and we're increasing by 50% every year. So, well, this number here, when we had our store that was while we had our store that was adding just some number every year was constant. This is a non-constant growth. We see here going from 255 to 506. We're not adding the same amount here as we are here. Here we're adding 281, but over here we're adding 633. That's a problem, right? So a linear function is not going to do here. Now, what I'm really doing is I'm multiplying by 1.5 twice, which makes sense because there's 2 years for every x value, and I'm supposed to be increasing by a total of 50% every year. So what I could say is my r is 0.5, and my b value is 1 plus r, which is 1 plus 0.5. So my b is 1.5. So in order to grow by 50%, I've got to take my starting point, right, which was 100, and multiply this by 1.5 x number of times to get to the number of stores that I have after x years. So with linear growth, you're going to have what's called a common difference. That means that we're adding the same thing each and every time. With an exponential growth, you're going to have a common ratio, which means that if you divide any output into the next, the quotient will always be the same. So as a perfect example of this, suppose we had 225 and 506, right? So if we had some sequence, and this sequence represented how many stores I have at a given time. And then what was the next one? 1139. If this was a linear growth, then what I'd be able to do to get from the 225 to 506, I'd be able to add some number and then add that same number to get to the next term. But the reality is that that's simply not possible. And we saw that on the previous slide. So adding isn't going to do it. But the question could be, well, what happens when I divide? So what I could do is take the 506, divide it by the previous term, right? And get 2.25, right? Hold on, is that true? Yes. Then, similarly, I could take the 1139, divide it by 506, and I end up with, wouldn't you believe it, 2.25. So another way you could even think about this, and the way that I tend to think about this, is common ratio, yeah, I guess, I mean, that's one way, I don't know. I don't find that to be the most intuitive way to approach it. What I'm saying is to get from this term to this term, I need to multiply by 225. To get from this term to this term, I'm going to be multiplying by 2.25, so on and so forth. If I wanted to go to the next term, well, I'd do the same thing, okay? Now keep in mind that from the previous slide, we ended up with a 1.5 per year. The reason we have the 2.25 for this slide is because we're actually listing off our sequence on every 2-year basis. So let's suppose we had a fox population in a certain region and we had an annual growth rate of 9% per year. It's estimated that the population in the year 2000 was 20,300 foxes. Okay, make sure that when you're doing this problem that you're keeping in mind that, you know, it's 20,300. It's a pretty big number, but there's a lot of foxes. So I know that R is positive because it's growth and it's 9%, so my R value is 0.09. Okay. I also know that my starting point is 20,300. So as you can see here, this is my starting point. This is my A value. My B value is 1 plus R, and my T value just represents X, where a T is the number of years. So this is my function that will help me figure out how many foxes there are for T years after 2000. Okay, T equals 0 for the year 2000. So we're going to use the function from part A to estimate the fox population in the year 2008. So in the year 2008, we have the T value being equal to 8. So all we're doing is we're just going to plug the x value in as 8. Okay, that's actually our t value. That's going to be p of 8. And we're going to do some rounding here. The reason that we round up is because we're talking about foxes. This notion of 0.02 foxes, that's kind of ridiculous. If we think about this, what we're saying is, well, so here's a fox. It's a fox. What we've got is 40,449 foxes, and then 2% of a fox should be just like a nose, just floating out in space. Well, we're not going to count that. That's just some nose floating out in space. That's not a fox. So rounding down is one way you could go about this, is one kind of thought process you could have here. You are not unjustified in rounding up as well. Either is fine. And Lumen doesn't mind if you round up or down. If it tells you to round up and you round down, it's going to have a problem. But otherwise, Lumen does not have a particular convention it's looking for. So here's a mildly more depressing example. So you've got a vehicle that we bought for $20,700. It's going to depreciate, meaning it loses value at a constant rate of 7% per year. For those of you who know things about cars, losing 7% of value each year is actually pretty generous. That's not bad at all. You need to determine the approximate value of the vehicle 11 years after purchase. Round to the nearest whole dollar. That's going to be where folks are going to make their mistake. One thing that's a lot of fun about teaching remotely is that you get a glimpse into each professor's life. And in the background, if you heard that sound, you heard my cat wanting to jump in and help out with the lecture. Unfortunately, I don't feel confident in my cat's ability to explain exponential functions, so I'm not going to let that happen. All right, so A is 20,700. My R is negative in this case. So the way Littman does it, and the way I don't mind you doing it, is we'll set R to negative 0.07. We're losing 7%. And so we construct this function here. Now, here's the way you can also think of it. If I'm losing 7% every year, you could also think of it as keeping 93%. And you could just write it as a decimal 0.93. Okay. So whatever works, okay? I like to think of it as, it's not that I'm losing 7%, it's that I'm keeping 93%. It's a pretty positive way to look at something generally bad that's happening, but there you go. Now, what I really wanted to compute here was V11. So now I'm just going to plug 11 into the function everywhere I see a t, and I end up with $9,317.14, which is kind of horrifying when you think that the vehicle was worth $20,000 or $20,700, and then a mere 11 years later, it's now less than half that value. But such is the nature of cars. So let's suppose I've got an exponential function, and it's going to look like this, and it's passing through these coordinates. I want to know what the values of A and B are. So I'm just going to go ahead and walk through the math of this. I want you to, just kind of wrap your head around where these numbers are coming from. So observe that in this coordinate pair, 0, 11, I've got here that x is equal to 0. That means that this value here is going to be my y-intercept, which I can also think of this as my starting point. So I know that A is equal to 11. Boom. So right out of the gate, I've got 11. And now I need to solve for B. So I've got that x is equal to 2 and y is equal to 176. I got this from my other coordinate pair. And now I'm going to solve for B. So I plug in these values. This is my y. Here's my x. And I end up solving for B. Now, I get that B is plus or minus 4. Our B value is always going to be positive for this course. Now, when you get to Calc 2, we could have a negative b value, and we could talk about the sequences and series that are derived from that, but that is not a battle for today. Some would argue that that's not a battle forever, so don't fret. It's always going to be positive. And then I end up with f of x is equal to 11 times 4 to the x power. So that's going to be my final function. Okay. Now, if you remember, it's going to be crazy. We're going to cycle through here real fast. We've already done the first objective, and we've done it with coordinate points and real world context. Boom. So we're doing it. We're moving right along. Now, there's one little thing I need to cover with coordinate points. Let's suppose, so here I've given you one where you're given the y-intercept. This one here is a little trickier because I'm not given a y-intercept. So what you're going to do is you're going to use each coordinate pair to get information. So we're going to start with this coordinate pair. I tend to start with the grislier coordinate pair. So I'm going to use this guy first, the -3 and 1/32. So again, this is my y value. This is my x value. So I know that it's an exponential function. It's got to look like a times b to the x. So I've got my 1/32 is equal to a times b to the -3rd. Now, as a note, something that you need to recall, b to the -3, well, that's equal to 1 over b cubed. And this isn't just like a magical thing that happens at 3. If I do that with any power, if I say like b to the -k, that's 1 over b to the k power, okay? So keep that in mind. That's something you may need to look up if you need to. So I solve for b, and I'm going to use, the way you don't see me do this is I use cross multiplication here. So I get 32a is equal to b cubed. I'm going to divide both sides by 32. And I get this little guy here. A is b cubed over 32. Now, I'm going to do the same thing, but I'm going to use the second coordinate pair. And what I'm going to do is I'm going to substitute this value of a in at the appropriate time. So here's my y value. Here's my x value. I've got 8. And now in the place of a, I'm going to put this in there. So there's my a value, and there's b, right? So now this b goes up to the numerator, and this becomes b to the 4th, because this is technically b over 1. And this is technically 8 over 1, so if you wanted to, what you could do is another round of cross multiplication. Okay. And I get b to the 4th is equal to 256. So now I'm going to take the 4th root of b. And again, since I took a 4th root, it's technically a plus or minus 4. But since we're in pre-calc 1 and not calc 2, we don't worry about the negative. And we end up with b is equal to 4. Now, since b is equal to 4, I can use the b in this equation here to find a. So I just plug 4 in everywhere I see a b in this little equation. And I end up with 64 over 32 is equal to 2. So my final answer is 2 times 4 raised to the x power. Okay, we're doing it. We truly are. Now we're going to talk about compounded exponential growth. All that compounded exponential growth really is where I take 5% and then I throw 5% on top of a pile. And then I take 5% of that new pile and throw that on. And then I do that 5% again and again and again. Ultimately, what's happening is I'm collecting interest on top of the value that's there. So what's really happening is the interest is reinvesting in itself. Okay, so this creates this nice exponential growth model, right? Now, here's the equation that we use for this. Okay. Now, here's the thing. A is going to be a constant. R, K, and T are also going to be constants. We may not know what those are. I'm sorry, R and K. T is not a constant. I'm being dumb here. So the only actual variable in this equation is t, and that's evident by this guy here. That's actually my input variable. This is going to be a constant, that's going to be a constant, and that's going to be a constant. Now, each of these constants means something. So the function a of t, what a of t means is how much is in the account at a given time. T is the number of years I've invested, so this is going to be my variable. And then the rest of these guys are constants. Now, keep in mind when I say constants, what I mean is it can only be one thing. It's not changing. So A is our starting value in the account. That's our initial investment. R is the annual percentage rate. You could think of that as our growth rate. You notice that I used a lowercase r just like I did earlier. It's the same thing. K is the number of compounding periods in a given year. So let's suppose K is equal to 1. That means I'm only going to gather the interest once a year. If I were going to gather the interest once a month, well, then K would be equal to 12. Okay. So let's suppose I've got $4,000. It's invested in a bank account at an interest rate of 10% per year. Find the amount in the bank after 5 years if the interest is compounded annually. Take a second and do this. Round to the nearest cent. All right. We know that A is 4,000. We know that R is 0.1 because it's 10% expressed as a decimal. And we know that T is equal to 5. Now, since we're compounding annually, the K value is actually going to be equal to 1. That's how many times I've compounded. Annually means just once. So I just quite literally plug these numbers into my formula. You are going to need to have that formula memorized. Okay, we are not going to be giving you this formula, which it's not that big of a deal. Just spend a little bit of time with it. You'll see that it's not difficult to memorize at all. Now, what we end up with is $6,442.04. So what we're saying is we've got $4,000. We invest it into an account with a 10% interest rate. And after 5 years, this is what we have. Now, I'll tell you, if you can find an investment product that has that 10% guaranteed, that doesn't require like $6 million invested into it, send me an email. Super important. I need that really badly. Now, find the amount in the bank after 5 years if the interest is compounded quarterly. So that's going to change things. Take a second and do that one. If you ended up with $6,554.47, you did this correctly. Here we're saying all the values are the same, but K is equal to 4. So everywhere I see a K in the formula, I'm just going to go ahead and put a 4 in its place. Okay. So think of the exponent as 4 times 5, that's to the 20th power. And this is what I end up with. Now that's interesting. This number here, 6,442 and 6,554, you'd think that they would be like, you know, when I compound the interest quarterly, that it would like blow up. There'd be this huge difference. And I mean, we're looking at like a little bit over $100-ish. They're not that far apart. That's interesting. Now let's suppose I compounded it monthly. Go ahead and do this computation for me. If you ended up with $6,581.24, you did this one correctly. Here our K is equal to 12 because we're compounding it 12 times a year. Now again, you'd think to yourself, why aren't these values blowing up? They aren't going to space, and you'd think they would be. 6,554, 6,581. That's like $27 going from quarterly to monthly. I'm compounding three times more often, but for whatever reason, I'm only getting $27 from that. That's weird. So here's here's a way that we can explain this. If I took my K value and I compounded it once, 4 times, 12 times, 365. If I did it hourly, there's 8,760 hours. Once per second, 31,536,000 seconds in a year. If I took $1 and I invested it into an account with 100% interest for 1 year, but I started to change the number of compounds, as I took my compound and the number of times I compounded and send it to infinity, right? If we think about the formula, it was A 1 plus R to the K over KT. What we just said was, okay, I'm going to invest $1. So that's my initial value into an account with 100% interest rate. That's kind of crazy. But the decimal of 100 is 1. And I'm going to invest it for 1 year. So that's just going to be T is equal to 1. So that's going to go away. Then this is the equation I end up with, which, I mean, now I don't need the 1 anymore. It's not doing me any favors. And so if I just did this computation, but I took this K value and I made it really, really big, what's going to happen is I'm basically going to get close to this number, which is close to that number if I had it less frequent. Ultimately, what this is called is asymptotic. What we're doing is we're getting really, really close to this number here, but never getting to it. And this is what's called Euler's number. Euler's number is 2.1 or 2.718, blah, 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 blah. It's just like pi. Pi is 3.14, blah, blah, blah. It's special, but it stands for a non-terminating decimal, meaning that it never repeats itself intentionally and in a pattern. Like it never continues to repeat itself. In the way of E, it's the same thing. Okay, it's what's called a transcendental number. It's an irrational number, and that number is very special. If you see E, it's not a function. It's actually 2.718, blah, 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 blah. Okay. So now let's talk about our fox population again. So let's suppose our fox population in a certain region has a continuous growth rate of 9% per year. That means that there's not like a set number of compounds of fox population. So it's not like foxes are mating and reproducing monthly. They're just constantly reproducing. Our formula is going to look like this. A, that's still our starting point. E, that's our Euler's constant. I'll write it a little bit bigger here. Okay. This is the Euler's constant, again, 2.71, blah, 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 blah. This is still our interest rate, and this is still going to be our number of years. So this is going to be my formula. Here's my starting point, still 20,300 foxes. Since it's continuous compound, I'm not going to have the, if this wasn't continuous, it would look, woof, what is that? It would be like blah, blah, blah from here. It's not going to be like that because it's continuous growth. So we know that that's when it's going to have the E. 9% is my growth, and there you go. So that's going to be our formula. So now I want to find the fox population in the year 2008. So I'm just going to take that equation and plug 8 into it. And I end up with 41,704.99 foxes. I'm going to go ahead and round that up to 41,705 foxes. Okay. All right. 4.2, graphs of exponential functions. Again, all we're going to do is talk about transformation laws as they pertain to exponential functions. Okay, so you're going to discuss components of exponential functions, their connections to their respective graphs, and we're going to perform transformations on these exponential functions. So ultimately what's happening is we've got this function a times b to the x. If b is bigger than 1, what's happening is it's blowing up. If b is in between 0 and 1, it's going down. Okay, now this picture is not drawn well. So this is if b is bigger than 1, this is if b is in between 0 and 1. Okay. growth or decay. The graph is always going to have a horizontal asymptote at y equals 0. Okay, this is unless it's been transformed. So if it's growth, we still have the horizontal asymptote at that particular, at the x-axis, at the line y equals 0. And boom, same thing here. Okay, so if it's growing or decaying, doesn't matter. If it hasn't been shifted up or down vertically, then we've got our horizontal asymptote at that point. And the graph will be concave up if a is greater than 0, and concave down if a is less than 0. Okay. All that means is if my starting point is here, boom, if that's growth, if a is greater than 0, if it's above the x-axis, if a is down here, right, that's going to be below the x-axis. Okay, so think about just if a is less than 0, what I'm saying is I took this thing and I reflected it about the x-axis. Okay, the domain is all real numbers. This thing goes all the way to the left and all the way to the right, and the range is, well, from 0, because it never actually touches the x-axis, all the way up. So here's some examples of exponential functions where I've changed the a value. So you don't see it, but for the green one, the a value is technically 1. So you see as I change the a value, what I'm necessarily changing is the y-intercepts. All of the a values perfectly match the y-intercept here, which is fine because if we think like a couple minutes earlier, we defined our exponential function to be a times b to the x, where a is the starting point or the y-intercept. Now, when I start to mess around with the b value, that's when interesting things happen. So when I start to mess around with this number, stuff happens. So here, let's kind of like parcel this up. Something I'm noticing about these b values, 3/2, you could think of that as 1.5. Here we've got, I don't know, 0.33, 0.5, 0.9. We notice for all of these values, they're bigger than 1. And what happens is all of these graphs are shooting up into space. Whereas here, all of these b values are less than 1, and what they're doing is they're shooting down, but they're trying to get to the x-axis, but they're not going to. Now, as my value gets closer to 1, it looks like it's still shooting down, just not in a hurry. And in the same breath, as these values get closer to 1, they're shooting up, but not nearly in as much of a hurry as, say, 3 is. Any transformed exponential function can be written of the form a times b to the x plus c. All that the b to the x does is guarantee that I'm looking at an exponential function. Remember that a can do a lot of stuff. So with a, what we can do is reflect about x-axis, and that's if a is positive. Okay. We can also do stretch and compressions. And then c, oh my goodness, sorry. And then for c, this is going to be my vertical shift. It's either going to shift it up or down. So take a second and just list off all of the transformations of this function. And when I say this function, what I'm really talking about is this function. I started with 1/2 x, and then I did a bunch of stuff to it. What are the things I did to it? So just make a list of them. Should have 3. Okay. So there are 3 things we're doing to it. The negative, right, my little red star. What that means is we start with our base function, and we're going to reflect it over the x-axis. Sorry about that. I stacked these in a weird way. So whatever. Mystery's gone. So the first thing I did was I reflected it over the x-axis because this is negative. Now I'm going to change the starting point to -3, which is really just another way of saying that I vertically stretched this by a factor of 3. Okay. And then +4, I'm going to move this 4 units up. So it goes 4 units up here. Okay. And so here's prettier pictures. Vertically reflected and stretched by 3. That's going to put us down there, which is exactly what we had here in the blue picture. And then we're going to vertically shift it up 4 units. That's 4.1 and 4.2. Good luck out there.